want you to remember for a second, a couple of videos ago we spoke about account addresses, public keys, and private keys. And we said that those were all hexadecimal encoded numbers. So even though they look like a string of numbers and letters, we can really think of them as being solely one large number. The hash that you see right here works in exactly the same way. So I can copy the hash, I can open up my JavaScript console in the browser, I can place a 0x, which instructs JavaScript that I'm about to place a hexadecimal number, and then paste the hash, and then press enter. So you'll see that this really is a base 10 number right here. We can think of the hash as being a number. Now, Anders had specifically said that we are looking for a hash that starts off with some number of zeros. Again, that's not entirely correct. What we are really looking for is a hash that is less than some target value. So 000F727 might be less than some target value that our algorithm is looking for. Well, let me show you an example of this in a flow diagram to just make sure it's really clear. All right, so on the left-hand side here, we've got some amount of data that will be input to our given block. And then next to it, we have that nonce value, which you can think of as being a counter variable. So on the first step through that proof of work algorithm, we take our data of hi there, we join it together with the nonce, like we literally stick those two values together, and then we hash the output, which might come out as this A230 blah blah blah. You can then imagine that behind the scenes, we take that hash right there, convert it to a base 10 number, and then we ask if this number right here is less than some target value. And let's imagine right now that that target value is 1000. We say, is that less than 1000? No, it's not. Okay, then we need to continue looking for another value. Let's increment the nonce by 1, do the hash again, convert that to a base 10. Is that less than 1000? No? Okay, let's keep going until eventually we end up with hi there plus a nonce of 5. That gives us an output hash of 0077 BBB. Maybe that is equal to 100. Okay, 100 is less than the target value of 1000. That means we have found a valid solution. So he is correct that we are kind of looking for a hash that starts with some number of leading zeros, but in reality we're actually looking at the value of the hash rather than just a specific number of zeros. I want to continue just a little bit more on this point, because it is a rather important idea that ties into a very critical aspect of the blockchain. So another way of looking at this is to imagine the entire range of possible hash values. The hashes that we are working with are 64 characters long. So right here, this is 64 characters right here. I can do a like this, let's wrap it inside of a string, and I can do a dot length, and you'll see that it is in fact 64 characters long. So if we imagine the entire range of numbers that can be encoded inside of that 64 character string, it can range all the way from all zeros, which would represent a base 10 value of 10, or it could be all Fs, which in hexadecimal would end up as being something like 1.15 times 10 to the 77th. A good way of imagining this is to imagine the proof of work algorithm as someone giving you a giant handful of dice, like 64 dice. Imagine holding 64 dice in your hand, and someone telling you, I want you to roll those dice until you eventually come up with a value of the dice that is less than like 100. Well, chances are you're going to have to roll those dice many, many, many times before you eventually roll something that totals up to less than 100. So that's the idea here. Now, I said that this was kind of a critical idea to wrap your head around, and let me tell you why. I'm going to expand on that just a little bit. So the entire process of rehashing the data along with the incrementing nonce takes some amount of time. Our computers can execute many, many, many hashes per second, like thousands, tens of thousands, hundreds of thousands of hashes per second. However, in the real blockchain, we are looking for some target values, or this kind of like comparison value right here, this less than 1000. We are looking for some very small target values. So that means that in practice, even though our computers can hash all this data very quickly, we have to execute so many hashes to eventually find that random number that is less than the target value that it ends up taking many seconds of time in the real world. We refer to the amount of time that it takes to hash everything from 0 to the target nonce value as something called block time. That's essentially the amount of time it takes to run these hundreds of thousands of different possible hashes until we find that final value that actually equates what we're looking for. So when we think back to the transaction that we executed a couple videos ago, where we sent ourselves some money, and that took like 30 seconds or so, that 30 seconds represented how long it took to run this proof of work algorithm to eventually find a solution. It was a block time of about 30 seconds. Now in reality, it was actually less than 30 seconds to run the proof of work algorithm, but once one individual node on the Ethereum network finds a solution, it then has to distribute that solution to other nodes. And so that additional amount of time is what eventually added up to the 30 seconds. Now there's just one last thing I want to tell you about the block time right here. The Ethereum network has a target block time of 15 seconds. So ideally, in a perfect world, to calculate one block, it would only take 15 seconds of time. And then the network would move on to calculating the next block or the next set of transactions to be executed. But in practice, that is entirely variable. So what's really happening behind the scenes is that kind of difficulty target right here. Remember I had said that we are looking for a number less than 1,000. This number right here ends up being adjusted over time after every single block is calculated. The network looks at how long it took to calculate the previous block, and it says, okay, if this was really high, or if it took way too long to calculate the block, then let's raise the target number. Because when we raise the target number, that makes it more likely that someone is going to find a solution more quickly. So in practice, you might see a flow that looks like this right here. Maybe we start off calculating block 100 on the network. And maybe we have a requirement that we have to find a hash that has a value less than 1,000. And let's imagine that with this requirement right here, it took the entire network 20 seconds to find a solution. So in this case, the network would say, whoa, hold up, that was way too long. It took us way too long to find a solution. We want to calculate a block within 15 seconds. So you know what? For the next block that we calculate, let's try to raise the difficulty limit. Let's try to find a value rather than less than 1,000, which might take a really long time. Let's just try to find a hash that is less than 10,000. So this kind of expands the window of valid hashes that we can calculate. But we can maybe imagine that when we expand that window up to 10,000, maybe the hash time, maybe the block time goes all the way down to 5 seconds. And then the network says, whoa, hold up, that's way too fast. Let's kind of decrease the limit now. And so we kind of split the difference between 1,000 and 10,000. And we now go down to 5,000. So we're trying to find a value or a hash that has a value less than 5,000 now. Maybe this takes 17 seconds. And so the network says, okay, this feels right, this feels good. And then we go on to the next step over here. And well, 17 seconds is good, but it still took maybe slightly too much time. So on the next block, let's try to find a hash less than 4,000. And maybe that then gives us 15 seconds here. Now you might be thinking, why is there so much variance here? Is there any variance? Why does it take different amounts of time? And why do we have to kind of adjust this difficulty target between blocks? Well, remember, the number of people who are running nodes on the Ethereum network at any given time is always in flux. People might be starting up nodes to calculate these hashes. Other people might be turning their computers off. So at any given time, the number of computers that are trying to calculate these valid hashes is always going to be changing. And so this difficulty target always has to be adjusted between every block to meet the actual computing availability of the Ethereum network. All right, now there's one last thing that I want to tell you about, just because it's a very interesting website that's going to kind of shed a little bit of light on what's happening here. So I'm going to put the link to it on the screen right here. We're going to go to etherscan.io. chart/block time. So this is a fantastic little chart that shows you the average amount of time that has taken to calculate these blocks over the last, 2 years or so. So you can see more recently, and chances are when you're watching this video, the graph will extend far into the future, but at least for me right now, some of the most recent block times are around 15 seconds. Now there was some point in time where they took all the way up to 30 seconds, but clearly something happened that reduced that down to about 13 and then back up to 15 or so. So you can always check out this chart right here to get a good idea of what the current block time is. And it'll give you some idea of how long it might take for a transaction to actually be computed and finalized by the network. Okay, so at long last, after a lot of discussion, we now have a good idea of exactly why it took so much time for that transaction to be completed and actually send some money from that faucet account over to yours on the Rinkeby network. So now that we have a better idea of what's going on with that, let's continue in the next video. We've spent the last dozen videos or so getting a handle on the Ethereum blockchain. I think that we've got a reasonable idea of what the blockchain is. We have an idea of how to create accounts using MetaMask and how to transfer money between people, or at least at this point, how it gets transferred on the blockchain. We're now going to start to talk about our next big topic, and this is going to be the topic that is going to dominate the rest of the course. That is a smart contract. Smart contracts are what we use to build interesting applications on the Ethereum blockchain. We're going to be writing many smart contracts throughout the rest of the course, and it's going to be a lot of fun because we're going to make some interesting apps. Let's first start off with a plain English definition of a smart contract. Right now, you can imagine a smart contract as being an account, just like the one that you and I created on MetaMask, but rather than being controlled by a human being like you and me, it is controlled by some amount of code. And this is code that you and I, or a developer in general, is going to author. This code instructs the smart contract how to behave. Let's talk about some of the different properties that are contained within a smart contract account. You'll recall that a while ago we spoke about some of the different properties that our accounts have, like say the public key, balance, and a couple like the nonce that counted the number of transactions that our accounts had. A contract account has a couple of different fields than the ones that you and I own. First, it has a balance. Well, our accounts have balances as well, but a contract account does too. This records the amount of ether that is controlled by this account. The next two properties are much more interesting. First is storage. Storage, you can imagine as being like a tiny little cubby where we can store some data that is related to our contract. This data is related to whatever application we're trying to build. So it can be numbers, it can be strings, it can be arrays, any type of data that is relevant to the application that we are trying to make. The next property that a contract account has is code. This contains all the raw machine code for our contract. So very machine level code that is almost impossible for you and I to read very easily. No, actually I should say completely impossible. The code that you and I write inside of our code editors are going to be compiled down to this raw machine code and then stored inside the contract account. So the contract account always has a good idea of exactly what it's supposed to do because its code and instructions are stored along with it. Now there's one last very critical difference between an account that you and I created and a contract account. The accounts that you and I created using MetaMask, you'll recall, over here on the left-hand side of this diagram, we refer to as external accounts. External accounts are any account that you and I, or a human being, or an entity owns. Remember that we had said that external accounts live in their own type of universe, and they're completely decoupled from any individual network. I can use the same exact account to connect to the main network, Ropsten, Covin, or Rinkeby. On the other hand, these contract accounts are only specific to one individual network. So when we create a contract account that contains our smart contract, we create it on one specific network, and they cannot be accessed across networks. So if I have some amount of code inside of this contract account right here that I deployed, if I wanted to access that over on Covin or Ropsten or Main, I would have to take this account, take all the code out of it, and redeploy it as a completely new account to these other networks. Again, there's no communication between these networks. So this is a little diagram of how we can start to picture these contract accounts. On our computer, or my computer and your computer, not our computer per se, but you get the idea. On your laptop, my laptop, whoever's laptop, you and I are going to author some amount of code that will serve as the contract's source. So this is the actual code that instructs the contract how it should behave and how it should handle money. We will then take that contract code, that source code, and deploy it to a network. like say Rinkeby. When we deploy this contract code, it creates an instance of the contract, or what we refer to as the contract account. We can take one contract source code, so like one contract file, and deploy it multiple times to one network or multiple networks. In that sense, you can really imagine the relationship between these source code files right here and these deployed instances as being very, very similar to the relationship between a class and an instance in the programming world. So if you've ever worked with JavaScript classes or Ruby classes or Java classes, it behaves in exactly the same fashion. So we can really imagine that the contract source code that we write on our computer serves as a class of sorts. It's a definition of the behavior of some object. We then create instances or copies of that class by deploying them to a specific network. A good example of this would be to think of maybe a tiny little demonstration class like this right here. So let's imagine that we have some class car. This is a definition of a car. There's no idea of one individual car. There are many instances of a car. So we can imagine this right here to be very similar to the source code that you and I are going to write on our machines. It describes how an account might behave. But to actually work with the car, we have to create an instance of it, just like you see down here. So we say we want to make a new car, and we're going to call this new car Mustang. You can imagine this Mustang right here as being or keep this idea of classes and instances in your head as you start to think about these smart contracts. Alright, so that's our first little taste of smart contracts. Let's continue in the next video, and we're going to start to dive into some of the different languages and tooling that we use to interact with these different contracts. So I'll see you in just a minute. There's just a couple more things I want to mention about smart contracts, and then we'll start to write our own. In this video, I want to talk about the programming language that we're going to use to write the actual code that gets inserted into a smart contract. For this, we're going to use a programming language called Solidity. Solidity was invented specifically for authoring smart contracts, and so it has many features inside the language to make the execution of these contracts much easier. Solidity is written into .sol files, and they're compatible with any standard code editor. So I particularly am going to use Atom later on in the course to show you how Solidity is written, but you're free to use any editor that you wish. Solidity is strongly typed, unlike, say, JavaScript, which is dynamically typed. If you've never worked with a strongly typed language before, that's totally fine. I'll give you a very strong refresher or an intro to how strongly typed languages work. Solidity is thought of as being similar to JavaScript. That's kind of a tough one. I personally don't believe it's that much similar. Some of the syntax certainly is similar, and if you're familiar with JavaScript syntax, you're going to have a very good time. But the way in which the language works is sometimes quite a bit different, so just keep that in mind. The last thing I want to mention about Solidity is that it has several very big gotchas. In general, if you're familiar with JavaScript and you're familiar with JavaScript syntax, you're going to be just fine writing Solidity after I teach you about some of these really big gotchas that you need to be aware of. In fact, if you're familiar with JavaScript right now, I could probably give you a list of like 15 big bullet points to be aware of, and you'll probably be quite productive with Solidity in very short order. The last thing I want to mention about Solidity is that the contracts that you and I are going to write and the contracts that are written for actual production applications usually end up being quite small for a variety of reasons. And so it's not quite so necessary to be a complete expert in Solidity, because we're not going to spend days and days and weeks and months writing just Solidity code. Usually we author a contract rather quickly, and then it's actually all the application code that we write around it, like HTML, CSS, and JavaScript, that we're going to write to interact with that contract. That's what usually takes the most amount of time. So again, don't be intimidated by Solidity. It's really not going to be a big difficulty hurdle. Now I want to speak a little bit more about how Solidity is used. When you and I write a contract, we're going to write what is called a contract definition using Solidity. Solidity is an actual programming language that is very easy for you and I to read and interact with and understand. but it's not the actual code that is actually executed on the Ethereum network inside of these smart contracts. Instead, we're going to take that contract definition and feed it into a Solidity compiler. This compiler is going to spit out two separate files. The first one is going to contain some bytecode, and this is the actual bytecode that will be deployed to the Ethereum network. So this is the actual stuff that gets stuffed into our contract account. On the other hand, the Solidity compiler is also going to spit out something called the Application Binary Interface, which we are going to refer to as the ABI throughout this entire course. This ABI right here is really key for writing applications that can interact with these deployed smart contracts. Let me give you an example. After we deploy a contract and get an ABI out of it, we're going to eventually write some JavaScript code that will serve as kind of the front end or the actual user interface to our contract. But our JavaScript code has no ability whatsoever to interact with the bytecode that has actually been deployed on the Ethereum blockchain. Remember, that Ethereum blockchain, the smart contract that exists there, it contains some bytecode that was previously Solidity. So you can think of the ABI right here as being an interface of sorts for getting our JavaScript code to understand exactly what's going on with this really strange, crazy looking bytecode down here. And that's what I'm trying to indicate with these crazy little symbols. Essentially, our JavaScript code thinks that this is all gibberish inside of here, and so we need this ABI to do a layer of translation for us. The ABI usually ends up as being something that's very easily legible, like you and I can read the ABI in plain terms, and it actually will give us a really good idea of exactly how we can interact with our contract. And so we will actually read the ABI several times to get a good idea of what functions or different pieces of data we can call and interact with inside of our smart contracts that we have deployed. All right, so that's just a little introduction on Solidity. Let's now take a break. We're going to continue the next video and start working on our first smart contract. So I'll see you in just a minute. I'm really excited because in this video, we're going to start writing our first Solidity contract. In order to write this first contract, we're going to use an online code editor called Remix. Remix is made specifically for creating and testing Solidity contracts. Now, I know that I said in the last video that we can use any type of code editor we want to work with Solidity, but in general, I personally like to use Remix a lot because it's got a lot of built-in tools for both auditing and analyzing your code, and in general, it just kind of works nicely. Now, later on in the course, after we work with Remix for a little bit, we'll eventually end up writing contracts inside of our code editor, but for right now, you'll get a really good idea of exactly how Solidity works by using Remix for a little bit. So it's a great place to get started. We can access Remix by navigating to remix.ethereum.org inside of your browser. And I really encourage you to walk through these steps with me. So inside of my browser, I'm going to navigate to remix.ethereum.org. On the page that pops up, you're going to immediately see a bunch of code inside of a code editor. And we'll do a full walkthrough on this tool in just a little bit, but for right now, we're going to focus on writing our first piece of code. So I don't want to use any of the code that's already in here. Yeah, there's a lot of code here, and we don't really understand any of it just yet. So here's what we're going to do. We're going to select the code inside of here. I'm going to select all of it with Command or Control A, and I'm just going to delete all of it. And we're going to start from scratch. So we're going to write a contract without any previous knowledge here whatsoever. Now for this first contract that we write, obviously we haven't spoken about syntax of Solidity or anything like that at all. So we're just going to write out a very short little contract together. Then we'll take a break, and we'll come back and rip this contract apart piece by piece. And I'll make sure that you are 100% clear and aware of every last little bit of syntax in this thing. So again, first part, we're going to just write some code out blind, and then we'll talk about it in great detail. Okay, so let's get started. I'm up here at line 1. We're going to start off by writing pragma Solidity. And do a little caret like so. We'll say 0.4.17 like so. This specifies the version of Solidity that we are starting to write inside this file. Next, we're going to define our first contract. I'm going to say contract inbox, and then I'll place a set of curly braces like so. Immediately underneath that, I'm going to declare an instance variable. So I'll say string public message. This defines a new variable called message that is going to exist inside my contract. It will be of type string, and it's public because it's going to be accessible to anyone in the world. Next, we're going to write a couple of different functions that are associated with this contract. Some of these functions are going to be a little bit complex, but remember, we'll talk about all of them in great detail in just a moment. So the first function, we're going to say function inbox. We're going to receive one argument that's going to be a string, and we'll give it the name initial message. I'm then going to close off this parenthesis. I'll write the word public, and then I'll do a set of curly braces. Now, if you're familiar with JavaScript at all, chances are some of the syntax is in fact feeling a little bit familiar at this point in time, which is good. Inside this function, I'm going to say message equals initial message. Notice how when we started writing out initial message right there, we got a little bit of autocomplete, which is a nice feature of the Remix editor. All right, two more quick functions, and we'll go over all this code together. So I'm going to say function set message. We're going to have another set of arguments here, which is going to be a string with an argument called new message. We're going to put the word public here again, and then put another set of curly braces. Inside this function body, we'll say message equals new message. All right, just one more function. We're going to write out a function called get message. We'll write out public, view, returns, and then string, like so. Make sure string is placed inside of a set of parens. We'll then place our curly braces and then say return message. All right, now at this point in the time, you should see a green little box over here. You should not see anything red. If you see anything red or any little icons along the line numbers here, that means you probably have a typo somewhere. So check out that line and compare your code with mine. One thing I want to point out is that every line that has a variable declaration or any actual line of code should have a semicolon at the end. The exception are these functions that you see. So no semicolons are required for these functions. All right, so that's our first little contract, but of course we just wrote a lot of code without having any idea of what's going on. So we're going to pause right now, we're going to come back in the next video, and we're going to tear this contract apart and get a really good idea of exactly how it works. So I'll see you in just a minute. In the last video, we wrote out our first smart contract. We now get to do the fun part, which is to tear this thing apart and understand every last line of code inside of here. So I took all this code, I put it into a diagram, and I labeled a lot of the different lines with some different notes. So we're going to go through this diagram right here and talk about every line of code. We'll first start off at line 1, where we had that pragma, solidity, and then some series of numbers right here. This specifies the version of Solidity that we are writing inside this file. When this contents right here, when this code right here is fed into the Solidity compiler, the compiler will look for this version right here. And then the compiler will customize the way it behaves based on that version. This is done to ensure that if Solidity ever goes some change in the language, like if some new feature or some new piece of syntax is introduced, all the previous contracts that we wrote with previous versions of Solidity are not going to suddenly break because they have older forms of syntax. Instead, the compiler will look at this version and say, oh, they're using a version from maybe 2 years ago. I'm going to make sure I don't try to use XYZ feature when I'm compiling this contract. So you can think of this pragma mark at the top right here as essentially being a version identifier to make sure we don't accidentally run the compiler in an inappropriate fashion. Down on line 3, we then make our first contract definition. And that's where we said contract inbox. The word contract is a key word, and you can think of this as being almost identical to whenever we define a class in Java, JavaScript, Ruby, Python. You get the idea. Remember, all these contracts that you and I are writing can really be thought of as being classes. And when we deploy these contracts to an Ethereum network, those deployed versions can be thought of as instances. So right now, we are essentially working on a class. And even if you look at the contract that you and I are writing right now, it really has the kind of definition or the structure of what looks like a class anyways. So the contract right here, that's the keyword that defines or tells the compiler that we are about to write a new contract. Right after that, we place the name of the contract that we're about to create. So you and I just made a contract named inbox. Directly underneath that line and inside this first set of curly braces right here, we defined a storage variable. You can think of this storage variable as being sort of like an instance variable. This is an instance variable that's going to exist for the life of the contract. When we define that variable, we use a couple of keywords here. So first is the word string. String is defining the type of variable that we're going to make. So we're saying that the variable message is only ever going to contain a string. So it will not contain a number, an array, or any other type of data. It's only ever going to contain a string. In a little bit, I'll tell you about all the other different types that we have available inside of Solidity. The next word that you see right here is public, and that specifies who has access to look at the contents of that variable. We'll talk more about the public keyword in just a minute when we start talking about functions. Finally, at the end of the line, we set the name of the variable. So we're saying that this variable should be called message. Now you will note when I said that we are declaring a storage variable right here, a storage variable is one that will be automatically stored with the contract on the blockchain. So that means whenever we change the value of message right here, the value that we assign to message will be automatically stored for all eternity on the Ethereum blockchain. And we can always pull our contract back up from the blockchain and look at the value of this variable right here. This is in contrast to local variables. Local variables are kind of one-time created when a contract is executed and then thrown away at the very end, and they are never actually persisted on the blockchain. In this course, for the most part, we will be making use of storage variables, but in some cases, we'll be using local variables instead, and I'll be sure to always point out the difference between the two. After that variable declaration up here, we then list out 3 different functions. So these are 3 different functions that will be a part of this contract. I want to point out in particular the first function. We said function inbox, and inbox was spelled with a capital I. Notice that inbox has the exact same spelling and capitalization as the contract name. Because the function has the same name as the contract, this function is regarded as being a constructor function. Constructor functions are automatically called one time when a contract is first created. So you can think of this first function right here as being invoked automatically when we deploy our contract to the blockchain. The other 2 functions inside this file do not have the same name as the contract. And so instead, these are functions that we can call on the contract after it has been deployed to the blockchain. Now functions are pretty interesting, so we're going to pause right here and then break down these different functions and talk about the syntax for each of them. So quick break, and I'll see you in a minute. In the last video, we started pulling apart our new contract called inbox. We left off at the functions down here. Let's now continue by talking about some of the different functions and what they actually do. We'll first start off by taking a look at the syntax of the getMessage function. So here's the getMessage function. We're going to take a look at some of the different parts of the function declaration. We first start off with the function keyword and then the name of the function. There's no big requirements about the name of any given function with Solidity. Just remember common programming sense. we want to make sure that if anyone looks at a given function, it's at least somewhat clear as to what its purpose is. In this case, we called it getMessage because it gets and retrieves a message that is stored inside of our contract. And so I think the function name was pretty reasonably picked in this case. After the function name, we list out some different arguments that this function can be called with. In this case, getMessage did not accept any arguments, so we left this set of parentheses empty. However, if you take a look back at our setMessage function right here, you'll notice that we specified that this can be called with one argument. That argument had to be of a type string. If it was called with a string, then that string would be assigned to the variable newMessage, and we could then access that argument from within the body of the function right here. In this case, if we ever try calling setMessage, so we left this set of parentheses empty or a number. However, if you take a look back at our setMessage function right here, you'll notice that we specified that this can be called with one argument. That argument had to be of a type string list. We list out if it was called with a string, then that string would be assigned to the variable newMessage, and we could then access that argument sometimes from this function public called with here. Other times, in this case, we'll see just the word public, and as a matter of fact, we just saw that a moment ago with our actual code. So you see right here we have public, over here public and view. So we're always going to have some number of words after the argument list. We refer to these as the function type declaration. There's a variety of different words that we're going to put in here, and let's talk about some of the most common ones that you're going to be using inside of your code. Alright, so here's a list of the most common function types. There's maybe 2 function types that I did not list on here, but in general, you probably will not be using those other 2 very often, and I'll leave it up to you to do a little bit of research if you want to find out what they are. Honestly, just really stick to these for right now. We're going to look at all the different function types that we can specify, starting at the very top here. The first one is public. If we mark a function as being public, that means that anyone in the world can call this function. And when I say anyone, I mean anyone with an account. So anyone with an Ethereum account can access our contract and call a given function. Now this is not really used for implementing any type of security per se. So just putting the public word in there doesn't mean that, oh, all of a sudden our contract is accessible by everyone and completely open, and then if we put a different word, all of a sudden it's 100% secure. As opposed to public, we can mark a function as private, and that means that only our contract's code can call this function. Again, private doesn't really implement any level of security. Instead, you should think of public and private as communicating to other engineers as to whether or not they should be calling these functions at all. A good example of this would be maybe we put together a helper function. Maybe we make a helper function that just does some tiny little task that is very specific to our contract. And we only ever expect to call that function from within another function in our contract. That would be a good example of where we might want to use the private keyword. Notice that we can only use one of these per function. So a function is either public or private. In general, we're almost always going to be using the public keyword unless we are making very specifically a helper function, in which case we might use the private keyword. The next two keywords right here really may mean the same exact thing. So this term used to be called constant. In more recent versions of Solidity, they have updated the name to be view. In documentation, you're going to see sometimes constant and sometimes view. Again, they mean the same thing, and you can use them interchangeably. Using the view or constant keywords inside of the function declaration specifies whether or not that function modifies any of the contract's data. So let's take a look at an example of this. Let's go back to our code editor over here. So in our get message function right here, you'll notice that we are not attempting to modify the message variable in any way, shape, or form. We're not changing it. We're just accessing it. Because we are just accessing data inside the contract and we are not trying to modify or change it whatsoever, we are making use of the view keyword right here. This specifies to the Solidity compiler that this does not modify any of our data, and it actually changes the way in which we attempt to call this function, but we'll see an example of that very shortly. On the other hand, we can take a look at the set message function. In the case of set message, we clearly accept some argument and then update or modify the value of the data within our contract. So we are modifying the variable message right here. So this function right here would not be appropriate to mark as either view or constant because it is attempting to change our contract. The next function type is pure. Pure is very much like view and constant, but it goes one step further. A function marked as pure means that the function will not modify or even access the contract's data. In practice, I kind of expect you won't end up using pure that often, except out of some pretty interesting edge cases. Or, I don't know, I'm sure you could contrive a good example or two. But in general, I personally have not found many instances where I might want to use pure. Now the last keyword that we're going to cover, and this is one that we'll use quite a bit throughout this course, is the payable keyword. The payable keyword means that whenever some outside source or some outside entity, like you or me, attempts to call a function on a contract, payable means that we might attempt to call it and send money to the contract at the same time. We're going to end up using payable quite a bit because a lot of the contracts that you and I are going to write are going to attempt to accept money from people. So we're going to expect that people somehow access our contract, and at the same time they do, we might require that they pay us some money for the privilege of running our code, so to speak. Okay, so this has been an overview of some common function types. Now you don't really have to memorize all these from the get-go. I'm just trying to give you a sense of some of the different things that you can expect to see with the language. As time goes on, and as we start to write more and more code, I promise you I will be telling you all the different function names that we'll be using. Now the last thing I want to point out inside of here is the returns keyword down on the get message function. Returns is used to specify the type of return value that we can expect to see back from a function. Returns is only ever going to be used on functions that are marked as view or constant. So if a function is meant to modify the state of the contract, a function that modifies the state of the contract will not return any values. Now to be clear, we can attempt to return a value. So if I say return message and then returns string, you'll notice that we don't really get an error message here. So that doesn't quite match up to what I just said about about functions that modify the contract data as not being able to return value. But in just a little bit, I'll show you an example of why we cannot actually return data from a function that modifies our contract. All right, I'm going to clean up that code really quickly. And we'll remove the returns right here as well. Cool. All right, so I think that completes a first overview of our inbox contract. But we still need to use the remix tool quite a bit to figure out how we can run, deploy, and test out this contract. So let's pause right here. We'll continue the next video and we'll get a better sense of how to use the remix tool. So I'll see you in just a minute.